Hello, my name is Brian Alvarez, and the topic I chose to do research about and to create my presentation on is the Fibonacci sequence. Before I get into the actual Fibonacci sequence and like the math relating to it, I'm gonna take a quick history detour, step back to talk about the man who invented the Fibonacci sequence. And the man who invented the Fibonacci sequence was an Italian mathematician named Leonardo Pisano Bigelow. And I apologize if I butchered his Italian name horrifically. But, anyways, you might be wondering, why is it named the Fibonacci sequence if his name is Leonardo? And, just using previous knowledge from any other rule from math, almost everyone who's ever created or came up with any type of rule or theorem names the theorem or rule that they created after themselves. So it's kind of weird seeing Fibonacci when the guy was named Leonardo, but he was also known as Fibonacci, which is where Fibonacci comes from, which is why he named it Fibonacci sequence, or it's named the Fibonacci sequence. And a little fun fact about him is that he is considered to be the most talented Western mathematician of the Middle Ages, which is pretty cool. Okay, so what actually is the Fibonacci sequence? The Fibonacci sequence is a sequence of numbers that starts at 0 and 1, and essentially it's where you add the last number to its sum of the previous two numbers. So we see here we start at 0 and 1, so we have 0 plus 1, which equals 1. Now, going off what I just said, we use the sum, adding that to the last number. So we have 1 plus 1 equals 2. And we just continue this sequence or this step essentially infinite amount of times. And just from this example right here, we have 1 plus 2 equals 3, 2 plus 3 equals 5. You drop the 5 down, you add the 3 since it's the last number before equaling the 5. You get 3 plus 5 equals 8. And then 8 plus 5 equals 13. Now, okay, now um, we have yet again the Fibonacci sequence, which is shown right here with the same example as the previous slide, but also this kind of weird looking seashell shape with a bunch of cubes kind of descending in size as we get closer to the center point, you could say, of the seashell. What this actually is, this is known as the golden ratio. And if you're an architecture student or have taken any sort of architecture, intro to architecture class, or just someone who really likes art or architecture, you've seen this before, or you've at least heard of it. Essentially, the golden ratio is this spiral with the cubes in decreasing order. Not decreasing order, but decreasing size as you get closer to the middle point of the seashell spiral. But as you can see, the numbers that are added into it kind of proves or kind of emphasizes the Fibonacci sequence. The 1 plus 1 giving you the 2 right here, the 2 plus the 1 giving you 3, the 2 plus 3 equaling the 5, and so on and so forth as you get these numbers just by following the example. So this is kind of like a misleading image. It kind of does seem that the Fibonacci sequence and the golden ratio are like the same thing, essentially. However, they are not, but they do have a kind of special mathematical relationship as the golden ratio can also be, I guess, percented or expressed as a mathematical number, which is approximately 1.618. And where the special relationship with the Fibonacci sequence comes from is approaches, as the Fibonacci sequence approaches infinity, you could say, if you divide, let's use this equation or this section of the Fibonacci sequence, for example, if you divide the 13 by the larger of the two numbers that you added, which is 8, you would get a number that is approaching or is close to the golden ratio of 1.618. And obviously, as you approach infinity, the number you get from dividing the two gets closer to that 1.1. Oh, sorry. That gets closer to that 1.618. Moving forward, kind of demonstrating where the Fibonacci sequence does come in contact with real life and not just on a mathematical um, aspect. We're shown 6 examples of the Fibonacci sequence, but since the Fibonacci sequence does have that special connection, as previously stated, with the golden ratio, it's better shown with the golden ratio kind of just plopped on top of it. One example that I really like is right here, the seashell, just kind of how you can see how perfectly it lines up with that golden ratio. Since I previously mentioned how the spiral kind of does seem like a seashell, or in the shape of a seashell. But also piggybacking what I said from the previous slide about um, hearing about the golden ratio, if you enjoyed architecture or if you're an avid um, art fan, is that architects and artists are obsessed with the Fibonacci sequence, specifically because of its correlation and kind of relationship with the golden ratio. Because the golden ratio is considered aesthetically pleasing, harmonious, and just naturally occurring, as we can see by the examples of the sunflower, the pine cone, the broccoli, and the seashell, and even the galaxy, as we can see right here. This is kind of a really cool one, as you can see how the mic. I'm assuming this is the Milky Way galaxy, as it kind of follows that spiral. But artists and architects use the sequence and the golden ratio as a framework to create balanced compositions in visually harmonious designs, which we see as. And here we have two very famous examples, one of architecture and one of art. On the left, we have the Pantheon in Greece, and on the right, we have the Mona Lisa. Starting off with the Pantheon, we can see how the golden ratio in relationship with the Fibonacci sequence does create that perfectly balanced, perfectly, aesthetically pleasing look, as we can see here as the Pantheon's outer columns and wall line up with the golden ratio. And as we can see here, we follow the spiral as it begins to kind of curl downwards and tighten. We see how it transitions from just the column into more of a wall into the actual roof right here. And then if we keep following it, we can see it once again come down from where the roof would be if it had not been destroyed just over the years from the natural weather and just natural disasters that happen during its time. We would see as it follows down and just continues that symmetry that just continues to be pleasing to look at just because of how symmetrical and how balanced everything is within ratio to everything else. Um, Moving on from that, we're presented with the Mona Lisa, and we can see how the golden ratio in relation with the Fibonacci sequence comes into play with creating the balancing and just that aesthetically pleasing visual when looking at the Mona Lisa. We see how the golden ratio kind of balances the nose, and then how the nose relates to where her chin is positioned, but also relates to where the peak kind of curvature of her head is, to also where the placement of her hand begins, or just how her hands lay naturally. just going off of that, we can see how the golden ratio really influenced this painting and how the golden ratio dash Fibonacci sequence really brought this painting to life with that just that beautiful balance and that beautiful, just aesthetically pleasing to look at. And that is all I have for the Fibonacci sequence, what it is, who created it, and how it relates to our real life and our surroundings, and not just in a mathematical form. Um, Thank you guys.